Hi everybody, and welcome to week 2 of Computers and Computations. This week we'll be focusing on the history of computation, and in particular we'll look at some overarching themes that have emerged throughout the kind of prehistory, pre-Turing of computation. We'll try and isolate these, and then hopefully later in the course we'll see that these become very, very relevant. So I hope you enjoy this week, and I look forward to talking to the students in class. Okay, so without further ado, let's get into it. Okay, so as I said in the introduction, my focus this week is going to be identifying some key themes that have appeared, or you might think are visible in some of the historical work on computation. So here's the order in which they're going to appear. So first we're going to be looking at how the same problem can be encoded in different ways, and this can give a different level of difficulty, particularly with number systems. We'll talk a bit about Babylonian and Roman mathematical systems. Secondly, we'll have some notion of unambiguous and effective procedure, so some idea of a way of purely mechanically determining the answer to a problem, and there's a question there of how to make this precise. Thirdly, we'll see that this idea of computational difficulty that appeared in theme 1, sometimes this can actually be useful. In particular, it has application for cryptography and ciphers. 4, we want computing devices to be flexible and compute multiple different operations. So we don't want to just have a different machine for every particular operation we want to do. 5, what are the differences, and are there any, between human and machine computation? And then finally, we'll finish up by looking at the Entscheidungsproblem. Now, let's start a little bit by talking about why we need notions of computation. So, mathematics, and especially geometry and arithmetic, are very useful for keeping track of amounts of objects, for basic engineering and prediction applications. So, some of the most mathematically sophisticated civilizations were able to produce, real impressive engineering feats on the basis of mathematical calculations figuring to their engineering. So, the pyramids constructed by the ancient Egyptians are a really good example of something that is a very impressive feat given the use of ideas from engineering. Okay. However, we have to identify that if we just work with perceptions, humans are not especially good mathematically, right? If we don't have some notion of computation. So an example here, let's fast forward to the present day. If I present you very quickly with 2 collections of objects, and I don't give you time to count or employ the kind of thinking we standardly think of as algorithmic, I don't let you count them up, pair them off, do any kind of sums with them. I just present you very quickly with two collections of objects and ask you to tell me what the sum is. Then you'll perform very, very badly. Even if you have some idea of roughly the number of objects that are there, say you know that it's under 100 objects that I presented to you, you won't be able to give me an accurate sum, right? And in particular, you won't give me the kind of sufficient level of accuracy that we would expect if we want to do, important engineering applications. Okay, and you can check out Dahana has a really wonderful book called The Number Sense for these kinds of examples of how humans perform given short presentations of objects. Okay, so we want to have some way of working precisely with larger numbers, or indeed geometric figures, that allows us to be precise with how we manipulate them in calculation. Right, so in dealing with these kinds of problems with human perception, various cultures throughout the world developed quite sophisticated number systems. So the Babylonians had a base 60 notation system, Egyptians had numerical hieroglyphs, Roman numerals are well known. Nowadays, we use Arabic numerals. Chinese and Indian mathematicians made some significant contributions to summing equations, among other things. And even plausibly the earliest known mathematical artifact, this is a bone with notches cut into it. This was discovered in Africa. So the use of numbers and number systems and algorithms for dealing with these systems is pretty ubiquitous across human cultures and throughout human history. So as cultures developed and exchanged ideas, some number systems were adopted for computation and others fell by the wayside. So a good example here is that nowadays we tend to use Arabic numerals, whereas Roman numerals were not adopted. And perhaps one good reason for this is that Roman numerals are very cumbersome to compute with. It's really hard doing computations with them, whereas Arabic numerals are comparatively easy. And in particular, something that was, in some sense, a technological development was the use of the number 0. Allows you to be a lot more precise with your new notation systems. So, for instance, if I want to write the number 101 and I have a 0, I can write 101. Okay, and this is unambiguously in base 10 denotes 101. But if I have no 0 notation, it might be that I have to, leave a gap there or something to denote the 0, and this can lead to obvious confusion. For instance, it's less obvious how my notation for 101 is distinct from my notation for 11, for example. Okay, so this identifies our first rough theme, right? And this will crop up later in the course. The same problem, encoded in different ways, can have a different level of difficulty. So if we consider Roman numerals versus Arabic numerals, Roman numerals, these are both designed to compute the addition of numbers, right? In some sense, they're different notation systems, but one is far more cognitively easy to work with. At least, and we might find later that depending on how you encode problems, you can have different levels of efficiency. Okay, so on the last slide, I mentioned using numerical systems as part of computation, and key to any such account is going to be the idea of an algorithm. This is going to be roughly the idea, and we'll discuss this below, of having some precise, unambiguous instructions for determining an output. So a particular example you might be familiar with is the kind of algorithm you see when you work at school and you have to do addition. So the familiar example where we add the columns, carry the 1, etc., and in doing so, come up with a way of precisely and unambiguously summing two numbers presented in decimal notation. Good. So there are other kinds of very simple algorithm we can consider. So here's one. So this is just an algorithm to determine if two finite collections are equal. Okay, so here's how it works. So you first remove an object from each collection, check if either collection is empty. If no, you just keep doing that until you keep removing objects until one of them is empty. And if yes, you check if both are empty. If both are empty, you say, yep, they're the same size. And if no, you say this is false. So here's a visual example of this. We take case A, where we do have two collections of the same size. And I just start, I remove an object from each collection. And then I check if neither of them are empty. Neither of them are empty. Do the same again. Neither of them are empty. Do the same again. And now I check if they're empty, or at least one of them is empty. One of them is empty. And in fact, both of them are empty, so I return true. In case B, on the other hand, we go through exactly the same, trying to determine, successively taking out objects from the collection. And then at the end, we check if both are empty. They're not both empty. I've got this little critter down here. And so I return false. Those aren't the same size. So let's see a more interesting example of an algorithm. This is a very famous algorithm called Eratosthenes' sieve. And this is a way for determining all prime numbers up to a given number n. So in this case, we'll work up to 21. So the first step is to write all the numbers from 2 up to n on your list. Step 2, add the least number on your list to your outputs and delete all multiples of that number. So in this case, we write 2 on our output list and we delete all multiples of 2. All right, so go through, delete all the even numbers. Good. Okay, then we continue and we take the least number left on the list and we do this until all the numbers are done. So our second number is going to be 3 and we're going to go through and delete all multiples of 3 that are left. Good. Next number is 5. We go through, delete all our multiples of 5. Okay, now we look. Now we've got 7, delete all multiples of 7. And the rest is all trivial in the current context. So we know we've got 11, delete 11. We've got 13, delete 13. 17 and 19. So this has given us, in fairly quick fashion, all the numbers from all the prime numbers from 2 up to 21. Okay, so these give us a picture, these algorithms, of the kind of thing we're looking for with computation. So an algorithm, we can make this rough definition that an algorithm or a procedure, possibly an effective procedure, is a finite set of unambiguous instructions to perform a specific task. Okay, and this seems on the one hand like a fairly good definition. We certainly know what these are when we bump up against them in everyday life, but this is not clearly a mathematically precise notion of definition, right? Or is this a precise notion of algorithm? I mean, finite is a mathematical term, but unambiguous, this is not a mathematically precise notion. Nor is the notion of task yet mathematically precise. So this is going to bring us on to the second theme. We clearly have some notion of unambiguous instructions and effective procedure, but how can we make this mathematically precise? And we'll look at this in future weeks. Another example where computation becomes very important is cryptography. So historically, several ciphers were used in order that if I try and send you a message, or record some information, and then this is discovered possibly by a nefarious party that I don't want to know what the message contains, I want some way of encrypting that message. So here's an example. This is the Caesar cipher. And what we do with the Caesar cipher is you just permute the the letters of the alphabet. So in this case, we're shifting each letter down 3 places and wrapping around in the case of the end of the alphabet. So A will get mapped by this function to D, for example. So I miss out B and C. So this is our representative for A. And Z, this wraps around, misses A and B, and we map Z to C, for example. And you can go through and do the other letters if you want. So an example, the phrase flower sweep, we can, if I send that to somebody and I don't want them to know what it says, I can use this cipher to make it this piece of much more gibberish looking sequence of letters down here. And if they know what kind of Caesar cipher I've used, or in fact, if they're quite clever, I mean, the Caesar cipher is not a tremendously difficult cipher to break, but if they have this information of how to unwind the information from the apparent gibberish, then they can compute what originally I intended to say. So the idea behind cryptography, even early cryptography, is the following. So I make something, or I encode some information that's easy to unwind in terms of finding the inverse of the function. That's effectively what we were doing on the last slide. Easy to unwind if you have a particular piece of information, but hard to unwind if you don't, right? So if you don't have the key to decrypt the relevant piece of information, it's very hard for you to do this. Okay. Now, as I said, the Caesar cipher isn't actually very good. It's quite easy to break, but we can still identify something that's going to be an overarching theme in some of the course, and that sometimes computational difficulty can be useful. So we spoke earlier about how one reason certain number systems fell by the wayside was plausibly because they were computationally very inefficient. There are cases where we actually want to harness this difficulty in some sense, right? So making something difficult to compute, or the assumption that something is difficult to compute, can be very useful in developing certain technologies, particularly with respect to things like encryption. Now let's move on to the early development of computing like machines. So Charles Babbage developed something called the difference engine. I won't go into the workings of it here. You can look that up in a textbook or on Wikipedia. But roughly, this was just a machine that could mechanically tabulate polynomial functions. Now, something that's interesting here is the difference engine was designed for a very single, very specific task. This contrasts a lot with modern computers, in that modern computers, I mean, it's almost a hallmark of them that they're incredibly flexible, right? You can design programs that will run on computers, and you can design them to do multiple different operations. In many ways, you know, the limits of what can be done by computers, aside from hardware issues, is a matter of creativity. It seems like you can do almost anything with these things. And in this direction, Babbage actually collaborated on something called the analytic engine. And this is one of the first places where we see the idea that we might have a machine that can change its operations based on the inputs given, or you have input data, but you also have a particular program you run. And this was taken up very strongly by Ada Lovelace, who made some fantastic contributions to programming by developing some of these first programs. And indeed, if you go away and read some of Lovelace's writing in her notebooks, she foresaw a lot of the versatility of computers. So Babbage was very focused upon the idea that that computers would be very useful for computing arithmetic type operations. Whereas Lovelace foresaw things like the possibility of generating graphics, things of this kind using computers. And this represents a very important theme that we're going to be looking at, is how versatile computers are and what we can and can't do with computers. So whether there are limitations on the kinds of operations that computers can perform. Now, the example of Lovelace and Babbage and the idea of the analytical engine and flexibility of computers or computing machines raises a very interesting philosophical question. And that's the idea of who or what computes, right? So for much of our human history, computation is indeed a human activity, right? It's something that people do. They follow algorithms. They sum things. They do this in order to do whatever they want to do with their computations, build pyramids or whatever, right? But it's something that humans do. However, it appears as though it's something also that machines do, right? And this is evidenced by the fact that you're listening to this on YouTube now. This is a machine doing the computation required to produce the video. There is not a little human critter sat in your computer designing all the relevant graphics you see and audio that you see on your computer right now, right? So it looks like this is something that we share with machines. Both humans are able to follow algorithms and do computations, but also machines are the kinds of things that follow algorithms and do computations. So here's going to be another overarching theme of the course. What are the differences, and are there any differences between human and machine computation? And is there anything that human computation can do that machine computation cannot do, and vice versa? Are there things that machines can't do that humans cannot do? Let's finish with a very famous problem raised by David Hilbert, and that is that there are formal mechanical rules for churning out first-order systems. So we know this, right? And it's maybe a little anachronistic, but nowadays we're very familiar with a bunch of logical systems. So you'll be familiar with predicate logic or propositional logic, and these have formal mechanical rules. So, for example, I have any old sentence A. I know that we have A implies B, so this is one sentence. If I know I have A, there's just a formal mechanical rule that says derive B. So you have if A implies B and A, then infer B, right? Now the fact that we can think of these rules of deduction as just kind of mechanical handle cranking, so to say, raises the question that if you just give me any old formula phi, so this could be any old formula, right, in first order logic, and some set of axioms A, right? So I let you know some collection of sentences, and let's suppose it axiomatizes, I'm aiming to axiomatize some mathematical subject matters. I'll give you the axioms of Peano arithmetic, for example, right? Is there an effective procedure for determining whether there is a proof of phi from A? So, given inputs A and phi, can I just do some sort of mechanical procedure that answers the question of whether there is a proof of phi from A? So this is known as the Entscheidungsproblem, or decision problem in English. And this is one of the most famous problems that was resolved via a close analysis of computation. And we'll see some discussion of that in future weeks. And in particular, how the advances provided by Church-Turing and others allowed us to definitively answer this question.